Hello everyone, welcome to my YouTube channel. In today's video, we'll go over glomerular filtration rate. Now before we do that, let's quickly look at the nephron. The nephron is the basic functional and structural units of the kidney. So a typical nephron has a Bowman's capsule, as has been labeled here, with the glomerulus inside. The glomerulus are a network of capillaries that forms a ball-tuft structure. Fed into the glomerulus are afferent arterioles, which brings blood into the glomerulus. Then blood leaves the glomerulus through the efferent arteriole. It also have tubules starting from the Bowman's capsule. You can see over here convolutions. These convolutions are called proximal convoluted tubule. And the proximal convoluted tubule plunges into this U-shaped structure called the loop of Henle. From the loop of Henle, the filtrate that is formed will swim up to the next side of convolutions called the distal convoluted tubule. By the time the filtrate gets into the collecting tubule, if not for the function of ADH, then urine would have been formed, and it will drain down through this collecting tube into the renal pelvis, straight down through the ureter into the bladder to be stored. So then today we want to look at how the filtrate is formed at this region. So let's look at this image here. We can see the glomerulus over here, and then a Bowman's capsule where the filtrate that is formed would enter. Now also take note of the fact that we have the afferent arteriole, which brings blood to the glomerulus, then the efferent arteriole, which takes blood from the glomerulus back into circulation. Now looking at the glomerulus in greater detail, we come to appreciate the filtration barrier, which makes this capillary very special. So unlike capillaries inside the blood-brain barrier, inside the brain, which has no fenestrations, there is a lot of fenestrations inside these capillaries. We can see this filtration barrier made up of this capillary endothelium, which has these fenestrations over there, the holes in them. So as blood is flowing through these vessels, water and smaller units or electrolytes will pass through these fenestrations. Then if it is able to pass through this basal lamina, the last barrier it will meet is this filtration slit, which is enclosed with these podocytes pedicels. Now together, these three layers form the filtration barrier, making sure that water and electrolytes, specifically positively charged electrolytes, are able to pass through the filtration barrier. All right. Now, essentially, we also want to understand that once blood is drained into the glomerulus, proteins and other large molecules will not be filtered. So you can see that the proteins and other solutes are joining through the afferent arteriole into the glomerulus. And at the end of the day, filtrate is formed, but the proteins are coming back into circulation. This is under normal circumstance. But in situations like when the glomerulus becomes infected, okay, then we are expecting that it will lose its integrity in filtering the most essential and retaining the large molecules. Once this is understood, let's go ahead to look at glomerular filtration rate. Now, to be able to understand glomerular filtration rate, there are three major factors that account for glomerular filtration rate. The first one is the net filtration pressure. Now, net filtration pressure basically looks at the Starling forces, that is the hydrostatic pressure, the osmotic pressure, which come together to form or give us a net pressure. The net pressure is what would account for fluid to be filtered from the glomerulus. Basically, glomerular filtration rate is the volume of filtrate formed each minute by the glomeruli in the kidneys. And as I said, it depends on the net filtration pressure. Secondly, the filtration membrane permeability that we talked about. I'm talking about the filtration barrier. Their permeability to the solute or the fluid that will be filtered determines the glomerular filtration rate, the volume that will be formed, essentially. Then lastly, the total surface area that is available for filtration to occur. Why is this important? Because in the instance of glomerular nephritis or glomerular sclerosis, it reduces the total surface area that is available for filtrate formation. So it's important that there is enough surface area for filtrate to be formed. So now these two factors come together to give us the filtration coefficient. So the filtration coefficient together with the net filtration pressure gives us the glomerular filtration rate. Let's look at the net filtration pressure into greater detail, which is the major factor that determines glomerular filtration rate. Now, the net filtration pressure, as I have aforementioned, will be the major factor which will be responsible for filtrate formation. It depends on the Starling forces, the hydrostatic and then the osmotic pressure, which gives us about 4 pressures I'm going to talk about here. The first one is the glomerular blood hydrostatic pressure. The second one is the blood colloidal oncotic pressure. Then we also have the capsular hydrostatic pressure. There is a fourth one called the capsular oncotic pressure. We are expecting that the capsular oncotic pressure should be 0 because the oncotic pressure or osmotic pressure usually is as a result of the solutes that is found within a fluid that creates a pressure preventing fluid from being moved or from being transported out of the medium. So in this case, we are expecting that a capsular oncotic pressure is supposed to be 0. So let's look at these pressures one after the other to understand what accounts for these pressures. Starting with glomerular blood hydrostatic pressure. If we go back to this diagram, you will notice that the afferent arteriole has a larger diameter compared to the efferent arteriole. Now, this dimensions or this orientation of these two arteries creates a pressure. So we have a big diameter bringing blood into the glomerulus and a small diameter artery sending blood away from the glomerulus. That difference in the diameter of these two arterioles creates the pressure. This pressure enhances fluid to be filtered from the glomerulus. It has a value of about 55 millimeter mercury. So take note, it is the difference in diameter between the afferent and efferent arteriole that accounts for this pressure. Now the second one is the glomerular or the blood colloidal oncotic pressure. We can call it oncotic pressure or we can call it osmotic pressure. Like I said, there are certain solutes within the blood. For instance, you have large molecules like proteins. Example is albumin inside the blood. Now the presence of these molecules creates an osmotic pressure. Just like we know osmosis, a hypertonic solution do have a higher concentration of solutes. So that higher concentration of solutes creates an osmotic pressure that permits fluid or water to only come in but not move out. So that is the same thing that is happening here. The blood inside the glomerulus also establishes an osmotic pressure. This osmotic pressure is going to oppose filtrate formation, whilst glomerular blood hydrostatic pressure is enhancing filtrate formation. It meets an opposition called blood colloidal oncotic pressure. Now there is a third or there is a final opposing pressure called capsular hydrostatic pressure. This pressure is rather preventing filtrate from entering into the Bowman's capsule. So capsular hydrostatic pressure is the pressure of fluid inside the Bowman's capsule. It also becomes an opposing pressure. So now you realize that there are two categories of pressures here. One is facilitating or enhancing filtrate formation. The other is opposing filtrate formation. So therefore, if glomerular blood hydrostatic pressure is opposed by these two, then to get my net filtration pressure, then I have to add these two together and subtract it from the glomerular blood hydrostatic pressure to give me my net filtration pressure. So if we are to put some values into it to give us perspective, say glomerular blood hydrostatic pressure is 55 millimeter mercury, then our blood colloidal oncotic pressure as a result of the solutes inside the blood is giving us a pressure of 30 millimeter mercury. Then the capsular hydrostatic pressure as a result of the fluid inside the capsular space is giving us 15 millimeter mercury. So 30 millimeter mercury plus 15 millimeter mercury will give us 45 millimeter mercury. If we subtract that from glomerular blood hydrostatic pressure, it gives us a net filtration pressure of 10 millimeter mercury. 10 millimeter mercury therefore becomes the resultant pressure which will facilitate filtrate from being formed. Now, once we understand this, let's go back to the glomerular filtration rate and use a clinical scenario as an example to understanding glomerular filtration rate. So we have this question. A patient's renal function is being assessed, and after the assessment, the following values were obtained for a single glomerulus. So first of all, we have the glomerular capillary hydrostatic pressure, which is the same as glomerular blood hydrostatic pressure of 60 millimeter mercury. Then we have the Bowman's capsule hydrostatic pressure, which is the same as the capsular hydrostatic pressure, 80 millimeter mercury. We have our glomerular capillary colloidal osmotic pressure, which is the same as blood colloidal oncotic pressure of 32 millimeter mercury. Then the Bowman's capsule colloidal osmotic pressure in this case is 0. Then our filtration coefficient, which is as a result of the surface area available for filtrate formation, and then the permeability of the membrane to solute, is 12.5 mils per minute per millimeter mercury. So with these parameters given, we are to first of all estimate the net filtration pressure acting across the glomerular capillary membrane. Then when we get this, we use that information to calculate the glomerular filtration rate. So let's try to calculate this. We have our glomerular blood hydrostatic pressure, and I'll write this here as GBHP to be 60 millimeter mercury. We have our capsular hydrostatic pressure to be 18 millimeter mercury. We have our glomerular or capillary colloidal oncotic pressure, which we will call BCOP in this case, to be 32 millimeter mercury. Our capsular oncotic pressure is 0 millimeter mercury. Then our filtration coefficient KF is 12.5 mil per minute per millimeter mercury. So our formula net filtration pressure is equal to glomerular blood hydrostatic pressure minus the sum of capsular hydrostatic pressure, blood colloidal oncotic pressure or osmotic pressure, then capsular oncotic pressure, which would essentially be 0 anyway. So here our GBHP is 60 millimeter mercury. So I'll put 60 here minus the sum of capsular hydrostatic pressure, which is 18, the BCOP, which is 32 millimeter mercury, and then our COP, which is 0. So when I put that together, I'll get 60 minus into bracket 18. What would 18 and 32 give us? This is 0. This will give us 50. So that will be 50. So 60 minus 50 gives us 10 millimeter mercury. So over here, our net filtration pressure, therefore, is 10 millimeter mercury. So this is what is going to determine filtrate formation. Okay. Now the next question says that using our information from A, we are to estimate the glomerular filtration rate. So with our glomerular filtration rate, glomerular filtration rate, GFR, is our net filtration coefficient, and then the net filtration pressure. Our filtration coefficient from the question that was given is 12.5. So our KF is 12.5 mils per minute per millimeter mercury, and we estimated our net filtration pressure to be 10 millimeter mercury. So therefore, putting all of this together, our glomerular filtration rate therefore is 12.5 times 10 millimeter mercury. So that gives us a value of 125 mils per minute of filtrate that is formed, because that is glomerular filtration rate, the volume per minute. So we get 125 mils per minute as our glomerular filtration rate. So this 125 mils per minute of glomerular filtration rate tells us that filtrate, or 125 mils of blood, is filtered each minute. So anytime blood goes through, or anytime there is renal blood flow, about 125 mils are filtered each minute. Now it doesn't mean that all the 125 mils are going to form urine, because we also have other stages in urine formation, like tubular secretion and tubular reabsorption taking place. So there's even a high probability that about 70 mils of this amount may be reabsorbed as water back into the blood, depending on the metabolic requirements of the body. There could also be the insertion of ADH, which is a hormone released from the posterior pituitary, produced by the hypothalamus. And when this hormone is produced, what it does is that when you come to the collecting duct I showed you the other time, it will insert aquaporins. And once aquaporins are inserted, I'll write aquaporins here, aquaporins. Once they are inserted, these are water channels, and they have the ability to reabsorb water back into the blood. So anytime you are dehydrated, these aquaporins, as a result of the release of ADH, would cause water to be conserved. That is why it is not any filtrate or the volume of filtrate that is formed that ends up as urine. So this brings us to the end of this video. Next, I'll talk about factors that regulate glomerular filtration rate. Alright. Thank you for watching this video. I'll see you in my next video. Bye bye for now.